Now we're going to do a little intro into logs, logarithmic functions, logarithmic expressions. Talk about how we come about with the definition of logs. Okay, so let's go back first to something we already looked at, and that was exponential functions. And let's look at the specific exponential function y equals 2 to the x. Should be a familiar curve to you, as shown here. Okay, x-intercept, no x-intercept, y-intercept of 1, and the negative x-axis as its asymptote, always increasing. Okay, we know there's obvious points that it contains as shown here. Okay, and we wish to find its inverse because surely we know it has an inverse since it is 1 to 1. That is, it passes a horizontal line test. So it does have an inverse, and if the inverse is should contain those points. So some generalizations that we remember about an inverse is that it's simply a reflection across the line y equals x. So let's see what it looks like. Okay, so here comes the inverse of this graph, y equals 2 to the x. And there's, again, some other additional statements which we recall about inverses. Okay. Now, generally speaking, inverse, as we say up here, shown up here, is just flipping the x and y's, right? Okay, when doing this, the x and y coordinates of the function are exchanged to become the new coordinates of the inverse. Okay, that being said, then we can generally flip the x and y's in general and solve for the new y. But notice we have a problem when we do that with 2 to the x. Y equaling 2 to the x, then surely its inverse is x equals 2 to the y. But where do we go from there? Because this is not possible for us to express this y in terms of x. So, hence the reason for bringing logarithms into the question. So here's a very basic idea which is going to come up again and again and again and again, and you need to be solid on this. Okay, all right. The expression x equals 2 to the y, which is the inverse of y equals 2 to the x, can be written as y equals log base 2 of x. Okay, or in general, any expression x equals, keeps losing the x equals a to the y, can be rewritten as y equals log base a to the x. Just keep saying that to yourself again and again and again and again because it's going to come up every time. Okay? In other words, again, an expression x equals a to the y is rewritten in logarithms as y equals log base a of x, or vice versa. Okay? We'll do some practice on the next page here. Okay? So here we have these expressions, these exponential function expressions, which we want to take and find their inverses and then express their inverses in logarithmic form. So it shouldn't be that hard of a task. And here we go. Okay, so y equals 3 to the x exponential is the exponential expression. I'm going to get rid of some of those. Sorry. Okay. And the inverse is expressed as x equals 3 to the y, which in logarithmic form is log base 3 of x is equal to y. The next expression, y equals 1/2 to the x, its inverse is x equals 1/2 to the y, expressed logarithmically as log base 1/2 of x is y. The next expression, okay, y equals root 3 to the x, its inverse, x equals root 3 to the y, logarithmically expressed, y equals log base root 3 of x is equal to y. Okay? The expression y equals 10 to the x, that's the exponential, it's expressed as its inverse as x equals 10 to the y, or y equals log base 10 of x. These will become known to us as the common log, okay, log base 10. Talk about that later. Y equals e to the x, inverse, x equals e to the y, expressed logarithmically, y equals log base e of x. This is going to become known as the natural log, and again, we'll talk about that later. Okay, so the assessment we make here is that C, all the values, all the expressions in column C are the same as column B. That is, they're just expressed as functions, but they're identical expressions for what they stand for. And what do they stand for? Well, they're inverses, right? So we recall that B is the inverse. Everything in B is the inverse of its match in A. And since everything in column C is the same as its match in column B, then the conclusion, transitive property, you know, if B equals C and A is the inverse of B, then C is the inverse of A. So here are the relationships between a function and its inverse, okay? Here's the log expression. Here it is expressed in alternate form, and here is the inverse from whence it came. Let's do some problems, okay? We're going to look at some of these problems, okay? The big idea here, y equals log base a of x, and that's what we're going to be doing essentially, is translating these logarithmic expressions into exponential expressions. So we recall y equals log base x is what? A to the power y is equal to x. A to the power y is equal to x. So log base 1.5 of 27/8 is y is the same as 1.5 to the y equals 27/8. And of course, then we can put those on a common base and solve for y, which is 3. Common base being 3/2, okay? Another expression, the natural log base e of e to the 47th is y, which means what? E to the power y is equal to e to the 47th. Well, obviously then y equals 47 since the bases are equated. Here's another one. Log base x of 9√3 is equal to 5 is to imply x to the 5th is equal to 9√3. Now, okay, this one was a little interesting, so let's see how we approached it. There was not a common base, so we're going to try to equate the exponents, okay? Again, at this point, this is a problem we've done previously. 9 is 3/2. 9 is 3 to the 2 power. √3 is 3 to the 1/2 power. So then this is 3 to the 5/2 power. So x to the 5th is equal to 3 to the 5/2 power. We can solve that by taking the 5th root of x to the 5th as well as the 5th root of this expression over here. Going through that, we find that the value of x is √3. Okay? These are some interesting problems we might pose to you in a little bit. Okay, so we're going to stop it right there.